Okay, next topic we're going to be talking about is system of conservation laws. And scalar conservation laws is has some already interesting phenomenon. It has shockwaves, which we never see before, and it also has characteristics. But you can really have some very complex phenomenons in system of conservation laws, and it is one of the primary motivations for using numerical methods, because analytical methods such as the way we analyze the speed of the characteristics, they basically fall apart when you have several variables coupled with each other. I'm going to show you a little bit of like some videos. They are from natural. They are like from the physical world. So I guess this is a case where you can just see water flowing, right? But somehow you see this as a shockwave. It's called a hydraulic jump. So this thing, as the flow speed go from faster than the speed of a surface wave to going the flow speed going slower than the speed of a surface wave. It's almost like going from supersonic to subsonic. There is a shockwave or hydraulic jump in the world of hydrology happening over here, and that phenomenon can be solved using a system of conservation laws known as the shallow water equation. It's a system of three variables solving for the x, y viscosity of the flow, and also the height, or how thick the water is. And the more complex is you get flow dynamics, supersonic flow dynamics, in this case a three-dimensional regime, and you can see all these complex three-dimensional shock waves evolving. In this case, this is a hydrogen jet in a supersonic cross flow, and basically you get a jet over here going vertical, and there is supersonic flow going over here. So these are other cases that are that simply we can't find ways to analyze using analytical methods, and numerical methods here gives us a really unique way to look into the physics of this phenomenon, and in a very efficient and detailed way compared to if you are doing experiments, which in a lot of these cases are very, very time consuming and potentially dangerous. Okay, so for example, I'm going to give you the Euler equation as an example of system of conservation laws. So the Euler equation deals with the conservation of mass, momentum, and energy. So for mass conservation, it basically tells you the ddt of the integral of density within the control volume, dV, right? So the integral of density in the volume is the mass. And conservation of mass tells you that if you draw a control volume, the increase in the mass inside the control volume has to come from somewhere, right? Mass cannot be created out of nothing. So it has to equal to the total amount of inflow or negative of the total amount of outflow. So here I'm writing the outflow because my normal is usually by convention points towards the outside of the volume, and dot with the mass flux. Let me leave it as a blank now. ds equal to 0. So what is the mass flux? How can you describe the amount of mass flowing in a unit amount of area in a unit amount of time? Rho v, yes. So the density of the flow times how fast the flow is coming in, right? So the denser the flow is at the same velocity, the more the flow is. And also the same density, the higher velocity is, the more flow there is. So rho u is the mass flux. And you can see the mass flux doesn't just depend on mass itself, it also depends on something else, u. Okay, so it is not a scalar conservation law because the flux depends not just on that variable, it also depends on the variable that is another variable that is conserved, which is momentum. So how do you describe the total amount of momentum within that control volume? Yeah, the integral of rho u within the control volume, right? That's a vector, right? That's a vector describing the momentum. It not only has a value but also has a direction. Now the tricky part is, what is the inflow of momentum? What is the outflow of momentum? It's n dot what? Yeah, rho u times u. And here I'm just going to write the product. It's kind of a tensor product. It's tricky because this equation is actually in 2D. It's actually two equations. And we also have two fluxes, an x and y flux. So we are writing here for a 2x2 tensor here, right? This is u tensor product with u. It's actually 4 variables. And also plus a pressure times like an identity tensor. This is because over the surface, the pressure actually acts as a force that contributes to the change of momentum within the control volume. And if there is no external force like gravity, if there is no body force, then this is equal to 0. All right. Now we can see that the momentum flux, yes, it depends on rho u, right? But it also depends on u, which is actually rho u divided by rho. So in order to compute the momentum flux, you need the variable in the mass conservation equation. Again, they are coupled. And also we have a pressure in this. What is pressure? Yeah, pressure is a force, but like pressure doesn't just depend on rho and rho u. It also depends on how hot the flow is. If you have the same density, same velocity, if you heat the flow, the pressure is going to be higher, right? That's so you also need the energy equation. I'm just going to write rho E, and E is the amount of energy per mass. So this is the amount of energy per volume. Integrate, it's the amount of total energy. And this is the rho E times U. Sorry, E is a scalar. It's not a vector. E is a scalar. So rho E times U. This is a vector. And also plus PU. So this is the amount of work done by pressure to the control volume. The S equal to 0. Okay, and this pressure here is a function of rho and U and E, right? So that if you have different flow, it's you get a different equation. For air, you can approximate this using ideal gas law, and there is an algebraic relationship in that. So this equation is closed in the sense that if you have rho and rho U and rho E, and with this algebraic relationship, you can compute the value of the flux of all these three equations. You don't need anything else to solve this equation. This is all you need to solve this equation. Okay, and now if you write the entire state vector, we call rho U, and rho E as into it's a 4-dimensional vector, Then the whole system can be described as d dt of integral of w dv plus this dot with a f of w. F is going to be a tensor of w ds equal to 0. And through the derivation we usually do from the integral form to a conservative form, we get the differential form of the equation partial w partial t plus the divergence of this f, which is an algebraic function of w, is equal to 0. That's usually what we see as the Euler equation, as written on Wikipedia and anywhere else. Okay, any questions? That's usually how we derive a differential equation from some physical principle that is written in a macroscopic sense. Okay. And we also have the shallow water equation. That's another example of a system of conservation law. So a shallow water equation uses so it's also a conservation of, so first of all, the water is practically incompressible in normal circumstances. So conservation of mass is equivalent of conservation of volume of water, and also momentum. So basically we are having two equations to work with instead of three in the Euler equation case. And the shallow water equation is naturally solved in 2D. So the control volume, so the conservation of volume is d dt integrated over area of the volume, which is the height of the water times it's actually d, let me write that dv. Basically, it's the integral of the height times the area, right? The water is high at some places, low at some places. So if you integrate the height over area, it's the total amount of volume, plus the surface flux of h times velocity, the surface normal, and the momentum is also conserved, and the momentum is hu. So the amount of course, the density is, which is a constant, dv is equal to the momentum flux, which is rho h u tensor product with u, and also plus the gravity force along the control volume, which is half of rho h squared times g. So that's kind of the average amount of pressure. The average amount of pressure is half of h times rho g. That's how much pressure you have in the middle of the water column, times h, which is the amount of area. Okay, so this is times ds would be equal to 0. And again, you can, if you know what is h and what is hu, you can compute the flux algebraically. Huh? Oh yeah, I'm missing a dot n. Yeah, thank you. Right, so this is the so what I write in the parentheses is the flux. Yes.